Okay, so now this has been written up, but I of course now also need to write it down. So you just seen that MDL, normalized maximum likelihood approach, is supposed to give you the same as base with Jeffrey's prior. So even though, well, part of these things have already been said this morning, and because now you know a little bit more about this, I thought I should say also a little bit more about it. What do I mean when I say Jeffrey's prior is the uniform prior on the space of distributions rather than the space of parameters? So, think again about these first order Markov models or any other model of two parameters. For simplicity, assume there's a unit interval. That this is your parameter space. Now, each point in the parameter space indexes a distribution. And the problem with ordinary uniform prior is that this, if you do a nonlinear but continuous transformation of your parameter space, you get a new parameter space. And then in a new parameter space, you also get a method for new parameters with distributions, which is one-to-one. But when it's uniform in the one space, for example, in this space, not be uniform in the other space. So the ordinary uniform prior is not a very meaningful concept. Now, what is Jeffrey's prior? Well, recall about the whole story. Actually, really everything hangs together here. Recall that when I talked about finite models, finite sets of distributions, I talked about. I said you could count them. This complexity term becomes the number of elements minus the total confusion. And by the confusion, I meant the probability that one distribution generates data, but that it looks different from that distribution. Now, this is a well-defined thing. If I just have a finite set of distributions, if I have an infinite set of distributions, like the very distribution, then almost always I will get a maximum likelihood estimator, which is not exactly true to the true parameter value generated in your data. And this probability is 1, but you can look at what is the probability that this thing is further than this thing, say it's further than epsilon. And in this way, you can make balls here, depending on epsilon. So you can look at, if I'm here, this is a particular parameter value, and I use it to generate data, then the probability that I get a maximum likelihood estimator, which is outside this ball, is smaller than epsilon. So I can make those balls over the whole space. And typically what happens is that the size of these balls, again, epsilon will be different in different regions of the space. So epsilon ball means that everything within that ball is confusable up to epsilon. If you are outside the ball, the probability that something in the center of probability according to the center of the ball that you get a distribution with a maximum likelihood estimator outside the ball must be smaller than epsilon. If you make these epsilon balls, typically happens that they will be small here. No, it will be big here. Then they become much smaller here. So the size of the balls very much depends on your space. So you can think of those as equally at the level epsilon distributions which you cannot distinguish from each other, so which therefore, from a logical point of view, you might just as well consider as one distribution. Now, if you do this for a fixed epsilon, and you really think of everything inside such an epsilon ball as one distribution, then a logical way to define a uniform prior would be to put a uniform prior in each little ball. Now, if you do that, you get actually something which resembles Jeffreys prior. Jeffreys prior is the limit you get if you let the ball size shrink to 0. And then you get here extremely small balls compared to here. So the ratio in density between here and here goes to some limit. So the Jeffreys prior gives it regions in the parameter space, which contain a lot of very different distributions. So regions in the parameter space, where if you change the parameter a little bit, you already get a very different distribution, which is easy to distinguish from the original distribution. You get a lot of balls, and you get a high prior. That's the idea of Jeffreys prior. So now you need screen back. Thanks. Okay, so you've seen 3 interpretations now of this normalized maximum likelihood. Just plain compression, then counting or geometric, Bayesian interpretation. And the 4th interpretation is it's somewhat different. It's somewhat predictive interpretation. This will allow us to link this, at least to some extent, to things like cross-validation. So how does predictive interpretation work? Well, first we realize that if you can think of coding as a decision problem, where you have some distribution over outcomes, really you have a code over outcomes, then you get an actual outcome, you have to encode it, and the smaller the code length, the better you do. So then your loss is measured by the code length. So for a given distribution, when interpreted as a code, the loss when you get outcome x is minus log probability of x. But you can also think of this as a more general loss function if you want to do sequential prediction of outcomes by specifying a probability distribution. Then this would be some way of measuring how well you predict outcomes. If you give probability 1 to the outcome, your loss is 0. If you give probability 0, your loss is infinity. Actually, this turns out to have several interpretations. There's also a kind of gambling interpretation. You can, there are gambling games, so from candy gambling, where if you play the game, then the loss you actually make in terms of money is given by the logarithmic loss. It's a bit more complicated. That's the idea. You can think of this minus log px as a kind of loss to measure how good the prediction is. Now, if this is your loss function, then you use Bayes, you use the Bayesian universal model, and you can realize that the minus log probability, which is minus log the code length for the sequence according to the Bayesian universal code, can be rewritten as minus log the product, the Bayesian probability for first I outcomes divided by the first I minus 1 outcomes. Clearly, if I multiply this over all n, then all the terms cancel except for this with an nth power, right? So multiply this with here I minus 1 and I minus 2, so that I minus 1 cancels. So this can be rewritten as this. Now I can pull out the product into the sum. To get minus log probability of the data according to this Bayesian marginal likelihood distribution is equal to the sum minus log the conditional Bayesian probability of the ith outcome given the test. Just notice that this is just the condition. You can rewrite this as conditional probability. It's a conditional. This is for the first I outcomes divided by the first I minus 1 outcome. So that's the conditional probability of the ith outcome given all tests. Now, if you interpret this thing as the loss you make, if you use the Bayesian distribution for predicting the ith outcome, conditional on the test, then this becomes the sum of the total loss you incurred if you sequentially predict the next outcome using the Bayesian distribution based on the previous outcome. Now, what is this Bayesian distribution? Of course, we've seen before, but let me recall. So, the Bayesian conditional distribution for the ith outcome given the first I minus 1 outcome is just this fraction. It's the Bayesian marginal distribution, integral of theta weighted by the probability data for the first I bits and the first I minus 1 bits. Now, it turns out that you can rewrite this like this. It's also equal to the probability of the ith outcome according to theta weighted by not the prior but the posterior. So you first look at all your data, then you construct, you go from prior to posterior. So now you get a much more peaked distribution, posterior distribution of all the parameters. Typically peak near the maximum likelihood point for the data. Right? That's your posterior. And then you take the weighted average of the predictions of the next bit according to theta weighted by the posterior. That turns out to be the same as the Bayesian predictive distribution. So what this says is that minus log probability according to the Bayesian universal model of the sequence can be thought of as the sum of the logarithmic loss you incur if you use the posterior based on the past for predicting the next outcome. And you do that, you sum that over all predictions. So you start with the first outcome, predict the second, that's based on the first two, you predict the third, based on the first three, fourth, etc. Now, it's a well-known theorem in Bayesian statistics, so-called Bernstein-von theorem, that typically for large n, your Bayesian posterior concentrates very narrowly, closely to the maximum likelihood. So if you have a Bernoulli distribution, for example, then if you have a lot of data and you have to take a uniform prior, then the Bayesian posterior will have its maximum at the maximum likelihood point. So the Bayesian posterior is a function of theta, of parameters. It's the maximum and maximum likelihood point, and then it looks like a Gaussian with a width of about 1 over the square root of n. So as n increases, it's very narrow Gaussian, very much peaked. So that if you predict the next outcome by weighting according to this posterior, which is peaked very close to the maximum likelihood, then the prediction you make will typically be almost the same as the prediction you would make with the maximum likelihood point based on the past. So for large n, large I should say, this prediction is about the same prediction as you would get if you take the maximum likelihood estimator of the past and use that to predict the next outcome. So this led Phil David and Bill Morrison to the same idea independently, also the same year, 1984. They said, now, what if it's very hard to compute this Bayesian marginal distribution? But it's easy, and there are cases like that, to compute the maximum likelihood distribution given the past. I can try then to approximate this Bayesian prediction of the next outcome given the past by the prediction of the next outcome given the maximum likelihood of the past. Or more generally, often the maximum likelihood estimator is very unstable for the first few outcomes. So I may also replace it by a Bayesian maximum a posteriori estimator or some smoother maximum likelihood estimator, as long as for large samples the estimator converges to the maximum likelihood estimator. So I have the sequential prediction game where I predict outcomes using some distribution, which is a distribution I'm allowed to use depends only on the past outcomes I've already seen. If I do this with the Bayesian distribution, then the total loss I incur becomes the log Bayesian marginal likelihood. And now I'm going to look what happens to the total loss I incur if you use another distribution to make the prediction, for example, the maximum likelihood of the past. Now it turns out that under regularity conditions, the sum of the total loss you make, the log loss, if you use this maximum likelihood prediction, so base your maximum likelihood of the past, you pick the next bit, and you add the total loss, is equal to the thing that would have given you the best predictions with hindsight. So this is the maximum likelihood estimator for the full sequence. And if you know that, you can automatically make the best predictions for the full sequence. This thing, if you use it all the time for prediction of the full sequence, will maximize the probability, therefore minimize minus log probability, minimize loss of the sequence. So the additional loss you incur by not using the thing which is optimal in hindsight, only using the thing which is based on the past when sequentially predicted, you miss something, of course. This cannot depend on the full data, only on the past. Something you miss is once again k over 2 log n, where k is the number of parameters in the model, plus the order 1 term. So this means that this predictive scheme can be thought of actually as a code. Remember that we think of codes not as things which have to have integer code lengths. They're just probability distributions over sequences. The minus log probability stands for the code length. It doesn't have to be an integer. So this thing actually defines a code and conditional on the past to predict the third, so you can build up the distribution for all sequences. This distribution can now be interpreted, check minus logarithm, as the number of bits needed to encode your data using a particular kind of code. And again, the additional number you need with this particular thing is equal to what you would have needed, the best thing in hindsight, plus k over 2 log n, plus order 1 term. So it is like a universal model, not the optimal universal model, where we minimize the order 1 term, but still almost as good as the best thing in hindsight, use predictive code. So this gives you actually two things. One thing is that if you don't use maximum likelihood, but you use the Bayesian posterior predictions, and it says that you can actually think of MDL model selection as fitting the model M such that total prediction error you make, if you predict the future based on past data using the Bayesian prediction, the Jeffreys prior, then you add the logarithmic loss of all outcomes. We pick the model for which the added logarithmic loss of all outcomes is the smallest. You do exactly the same as with MDL model selection or Bayesian model selection, the Jeffreys prior. So it gives you a predictive interpretation of what's going on, which is similar to cross-validation. But it's cross-validation with the logarithmic error, where the error you make in a prediction is minus log logarithmic sign of the prediction. And the difference with cross-validation is that here what you do for each model is you get the first outcome, you predict the second. You look at the first two outcomes, you predict the third, first three, predict fourth. So you predict each outcome exactly once. In cross-validation, you split the sample in different parts. You create an estimator, for example, a Bayesian estimator based on one part, and you predict the second part, and you do that for several splits. So, and usually you select splits randomly. So cross-validation, you may end up predicting the total cross-validation score. You predict the same outcome several times sometimes. So you predict everything exactly once sequentially. Actually, this way of doing things, so then with the maximum likelihood predictor rather than the Bayes predictor, has been known for a long time in statistics as forward validation. And so it's the fact that you can also do it with the maximum likelihood estimate, it gives you also a second interesting thing. It means that this gives you a way to approximate the normalized maximum likelihood code or the Bayesian code. If you plug in maximum likelihood instead of the Bayesian distribution, you still get a universal model, code lengths close to the codes you would have gotten if you would have used the full Bayesian approach to Jeffreys prior for the normalized maximum likelihood. See, this has been used a lot in time series model selection. Yeah?
You have mentioned that several times, but Jeffreys prior for the spouse dog, but I failed to see where it actually features.
You would have to use it in your, so you could use it with another prior as well. Say that if you would pick Jeffreys prior and you would do the sequential Bayesian prediction, then the total loss you would make would be exactly equal to minus log Bayesian marginal likelihood with Jeffreys prior. You could pick another prior as well. So Phil David has his own theory of model selection, somewhat different from MDL, and this is basically where the two things meet. So this can also be seen as a special case of so-called frequential validation. Frequential validation is like cross-validation, but with this idea that you predict sequentially, given each output at once. So that's the fourth interpretations, and I hope that these four interpretations get the idea that actually doing something reasonable, MDL model selection. So of course I also have to tell you, what do you do if you are in an actual model selection situation? So you have a finite set of models, you want to select one of those for your data. So then the best thing to do is to use the normalized maximum likelihood distributions or the non-informative Bayesian mixtures. Typically from the numerical experiments that I have seen, they give almost the same results already for quite small samples. Often you can compute that. Remember that the normalized maximum likelihood involves an exponential sum, exponential many things. In some cases there are tricks by which you can, the sum collapses and it gets numerically computable, but in many cases it's still not clear how to compute it. So that computationally pure minimum description length approach, where the complexity is measured as this log of the exponential sum, is infeasible. The basic mixture is also that involves complicated integrals. Sometimes you can do it, sometimes you can't. So another thing you might try, which in practice seems to give pretty good results, is use this predictive MDL, where you do sequential prediction and you report a minus log probability error. But you shouldn't take the maximum likelihood estimates, but some kind of smooth versions of that. I'm not going to go into that here. If that's computationally infeasible, or some other you don't want, you might use two-part code MDL, where you encode parameters first explicitly and then you put data on the parameters. We've seen that two-part code universal model is not the minimax optimal universal model. So intuitively you use a less efficient code for your bits, which at least for some sequences will give you more data, if you need more bits to encode the data. For some other you might need less. But you lose this property that you treat all parameters in your model the same way. You're bound to give preference to some parameters in your model. So this code is kind of a little bit more arbitrary. The goal of this normalized maximum likelihood, the minimax optimal code, is to really treat all parameters exactly the same way, and to be very honest towards everything inside the model. So if you do that, you should use clever codes, two-part codes, which make your two-part codes as close as possible to the minimax optimal normalized maximum likelihood model. That's also often not so easy. Now, if that also fails, or if you just want to do something easier, you can use this asymptotic expansion. So for all the models you want to compare with each other, you compare this minus log probability of data according to maximum likelihood plus k over 2 log n plus this curvature term. And then you pick the model for which the sum of those three terms is minimized. Now, that has actually become quite popular in the last few years for example, in experimental psychology, where people do a lot of model selection. I'm myself a bit wary of it because I have seen examples. The thing is, you don't know how much data you need before you reach the asymptote. For Markov models, people did simulation that works very well. This approximation is very good. But for some other models, it seems to work pretty badly, and then you can get very confusing results. Because you have a small O1 term, you don't know how big that is for the sample size you have. So you have to be very careful there.
That slide that was from the integral of the determinant and so on?
Yeah, so there's another problem there. But you can approximate it with some numerical integration, which is what they do. So if everything else fails, you can actually just construct a universal model. So for example, if you use a model which is not like the models they often use in statistics, and it doesn't have all these nice regularity properties, you can still do this. You think, okay, my model contains this and this distribution. I'm somehow going to come up with a code, so no matter what data I get, I don't use a lot more bits than the best distribution in my model does. And you're completely free to do that whatever way you like. Just try to do it so that you are treating all distributions in your model about equally well. Sometimes that will be not possible, so that you might expect that it doesn't work as well as before. But still, you can try to do it and do model comparison of that self-constructed universal model. So with large O n of 1, I mean that it should at least be a constant from the minimax optimal universal model. So no matter how much data you get, the amount of extra bits you use compared to somebody who uses the optimal minimax universal model should not grow to infinity. So then there are also computational issues. First, the good news. I've very often been asked by people like, how can you ever use MDL because you have to make all these codes for your data, which is very complicated. Well, don't worry, you never have to do that. We're only interested in code lengths. We want to compute how many bits we would need if we were to use a certain code to encode the data. But we're not actually going to encode the data. So encoding the number of bits we would need is a lot easier than encoding data itself. So this is one where we don't have, rather we have to compute some more standard statistical things like maximum likelihood estimators or integrals over likelihoods. Another issue is if you compute the base, want to compute the basic universal model, then often you can do the integral, so then you might do the same thing as for basic statisticians. Often you might try to approximate it to the Markov chain Monte methods. If you want to compute the direct thing, minus log probability of data according to maximum likelihood, plus log this enormous sum, then the first term, so that's this thing, and the coordinate which is likely maximized, they're typically easily computable for exponential families. So many families like Markov models fall under that, so normal families. Then you can either do it analytically, sometimes you can do it analytically, for example in logistic regression, but then at least for exponential families you always know that the likelihood surface is concave. So you can use local optimization methods like that. However, if you use non-exponential families, like for example Gaussian mixtures, as your model, then the likelihood surface may have local minima or maxima, and it's often hard. Nobody knows how to do it. To find the global maximum likelihood point in the likelihood surface for a given data. But then you can use some local methods to find local maximums, such as expectation maximization, your own favorite local maximization method. But now there's a problem. This is kind of important from a conceptual point of view. If you do that and you take all this seriously, then you should also, if you take a local maximum in the likelihood space, likelihood surface, rather than a global maximum, you should also change your complexity term. Because the complexity term was the sum of overall sequences, probability of that sequence according to maximum likelihood. That should now be changed by the sum of all sequences, the probability of the data, according to the estimate you will come up with for the data, which is not the global maximum likelihood, but the local optimum. So the sum will be a lot smaller because you have a local optimum here, not a global optimum. And this is, I think this is right, because if you use local optimization methods, you don't find the best fitting distribution for your data, so that effectively you have less expressive power in your model. The model is less complex. You run, actually it's well known. For example, if you use TM and you do early stopping, you run less risk of overfitting. Because basically you make your search space smaller. Something like this happens here too. So, from a theoretical point of view, I think this is kind of common. But from a practical point of view, this is really a problem. Because nobody knows how to compute it. This is not really the maximum likelihood scenario. It's a local approximation.
Yeah. You mean you are not at the maximum but close in the same basic fraction, in the same row?
No, I mean you're
Or
really. I mean this. Yeah. I mean you're
but
really.
these two are separated by finite. In the sense that doesn't that give you an exponential decay for all the other local minima? The probability is exponentially small.
Compared
no?
to the global, it will be exponentially small. But as long as you don't have the global, you can use that. Okay, so last point about this, it's certainly possible and arguably the most interesting application if you combine models in completely different forms, but the same number of parameters. And this has been done in recent years in psychology. So an example is, for a long time, currently a debate in psychology or psychophysics about how to relate the strength of a physical stimulus, for example, brightness of a light, with the perceived stimulus. So you have the light, you turn it on brighter and brighter, and you ask people on a scale of 1 to 10 to say how bright they think it is. So how does the perceived strength compare with the actual strength? One model for that is Spector's model, which is logarithmic. Another is Stephen's model. It has been observed many times that for if you do this with small amounts of data, and in psychology you have to pay your subjects to do experiments. So usually they have sample size 30 or so, very small. That typically, in many experiments, even small better fits the data. And then if you tested on new data about the same experiment, fitted factors model turns out to work better. But we never understood why that was the case, because both the models have the same number of parameters. And so it turns out that if you use MDL, you see that the expressive power measured by this log, this enormous sum, the total fit between all the science data, is much larger for Stevens' model. It's a power law, and power law has a much larger power to fit data. Okay, so now we're going to go somewhat more generally. We can extend this difficult bit. So, first question that arises, what if I don't compare a finite number of models but an infinite number? For example, I look at all market chains of each order of my data, or all polynomials of each degree. Another problem is when you don't just want a model, you also want the parameters for your model. What does MDL say to do? The third and most critical problem is that for very simple models, this complexity term may become infinite, and then the whole procedure gets undefined. So I'm going to look at those three problems here.
Just a very basic question. Until now, you always spoke about distributions which you can parameterize, but I mean, if I have, let's say, a non-parametric approach, then I can't use MDL or...
You can still do this, but I'm not going to go into it. You can use the same basic type. You can have basically non-parametric universal models. Typically, they grow faster than logarithmic. They grow like on the order of n to the power 1/3 or something. But well, I think we should discuss it offline. But it requires a little bit of thing, but then you see that basically the same ideas. It's all still possible. So what if you compare infinitely many models? Well, first, finite. Well, this is what we did, right? Take minus log for each data according to the normalized likelihood. Minimize this over all models on situations. Now we're going to reinterpret this the moment you see one. We're going to now design a new code for our data. Now we first encode the model we are going to use to encode our data. And the model has an index between 1 and k. So with a kind of honest uniform code, which doesn't prefer any of the models, we use log k this to do that. So we first encode the index of the model, and then we encode the data using the optimal universal model relative to the model we decided to use. And then we need first the number of bits to encode the index of the model, and the number of bits to encode the data given the model. And this term, if we use this uniform code, this term will be a constant. And now we're going to use something which is a hybrid between minimax optimal unit, minimum description length, and using a two-part code. We're going to pick the model, but then the total code length needed to encode the data is minimized. So we have one code where we first explicitly encode what model we're going to use. Then we're going to use optimal universal code, that's the model. And we take the model minimizing this two-stage description of the data. Now, because we take a uniform code here, if we do this, we get exactly the same as if we do this. Right? Because this will be constant for all I, log k. If you minimize this, it doesn't play a role in the minimization. It doesn't become an I, you drop it. And this thing picks the same as this one. So why would I want to do this range reinterpretation? Well, if I compare infinitely many models, I have to do it this way. So then I should somehow first encode a model index. For example, the degree of the polynomial I look at, or the order of the market change. Now, because there's an infinite number of possibilities here, I cannot use a uniform code which gives each of them the same length. Right? There's no uniform code for any number of things. But I can use something which is like almost as good, which very slowly goes up as the index increases. For example, there exists codes that the number of bits I need to encode number I is 2 times the logarithm of I. It's very easy to construct such a code. Then this becomes 2 log I. And now, so I pick the most number of bits needed to encode the index of the model plus number of bits needed to encode data, given the model is minimized. And why do I have to do it this way? Well, suppose I simply do the same thing as before. I simply pick the model minimizing minus log probability today to given the model. Now you can imagine some extreme cases where this does something very strange. Namely, if all the models under consideration are singleton models containing just one distribution, and that's something we definitely don't want to rule out, then this may lead to terrible overfitting, because then you simply pick maximum likelihood distribution for your data. So if all the models contain just one distribution, and the normalized maximum likelihood probability for data according to the model, it's just the probability for data according to the distribution in the model. So then you have a countable set of distributions. If you would ignore this term, you would simply pick the distribution, maximize the probability of the data, minimize the minus log probability. So you would use maximum likelihood of a countable set of distributions. That is a recipe for overfitting. Think, for example, about the Markov chains. I can easily make a countable subset in a set of all Markov chains of each order, where I associate with each natural number the Markov chain with rational value parameter values, because Q, the rational numbers, countable sets. I can bring it in one-to-one correspondence with the natural numbers. I can actually come up with a countable set of distributions which include all Markov chains with rational value parameters. So this includes all Markov chains that will ever be the maximum likelihood distribution for any given set of data of every order. So this means that if I get data of length n, and I use this without correcting for the number of bits needed to encode the index of the Markov chain, I will always pick the maximum likelihood distribution within all Markov chains for the data, which for data of length n is typically a Markov chain of order n, and I haven't gained anything, I'm overfitting again. So in this crazy case, where all the models contain one distribution, you should make sure that you don't overfit, and you get this by once again, but then this, if you do it like this, you will get a two-part code. You would first include an index of the distribution, and then data using an index. Now if the models contain sets, are sets of distributions, this typically won't happen, but still, to stick with the general idea that you do inference in terms of coding, it seems to make sense to think of it, to first encode the index of the model, and only then encode the data using the model. So this brings me to the first part of the formulation of the general MDL principle. It says that we have a given set of candidate models. Models can be families of distribution, but also single distribution. Doesn't matter. So the first thing always do is to devise a single code which allows you to encode all sequences of data. And then you do all inference based on the code. So in case you want to do one selection, your code is first a two-part code where you first encode the index of the model, and then you encode data using the universal model for the index. And you'll see that if you do this, you get kind of a coherent grand picture. But this seems strange because I told you don't use two-part code lengths, you don't achieve minimax optimal code lengths, right? You should not encode parameter values or model indices explicitly. Now I'm doing it after all. Now why is that so? Because I want to use my procedure to select a model index. So if I want to use my procedure, which consists of trying to compress data as much as possible, to select something, then that something has to be encoded explicitly. So I can select that specific something which gives me the smallest code length. So that's what's going on here. We don't encode the parameters explicitly, because given the model, we're not interested in the parameter values. Then we use the min-maximum version of optimal to encode the data given the model. No explicit encoding of parameters. But we do encode the model explicitly, or the index of the model, because we want to select the model. So we need to explicitly have a notion of that. But indeed, next point, if you want to use MDL for parameter estimation, another thing you often hear, people think that MDL just tells you to pick for a given model, say all variability distributions. MDL will just tell you to pick the maximum likelihood estimator. Doesn't. Instead, what it does, it says, okay, you always want to encode your data relative to the model. So you should use a universal model relative to that model, but you want to find a parameter estimate for the data, so then the parameter has to be encoded explicitly. So now I'm going to use a two-part code, after all, for encoding the data into the model. And then it turns out what MDL will do is it will give you an estimator relative to the model, which is something like a truncated maximum likelihood estimator. It's a maximum likelihood estimator cut off to some low precision. Example, you have to create a new model, one parameter, very simple, on the unit interval. So we call it, when we developed the normalized maximum likelihood code, we were looking for the code among all possible codes of sequence of collected n, minimizing the number of bits needed to encode the sequence minus the number of bits needed to encode the sequence according to the maximum likelihood distribution for the sequence. And the solution to this was the normalized maximum likelihood code. Now we do the same thing, but we constrain the codes to be codes so that the coding happens in two parts. First encoding the theta, an index, and then encoding the data using the code corresponding to the index. So because among all codes which look like this, we look for the one which has the best minimax optimal properties. This gives me a code which for every sequence of x's I can get, gives me a particular value of theta which I will use to encode the sequence. And that is then my MDL estimator relative to the model. Notice this is not the maximum likelihood estimator. Why is it not the maximum likelihood estimator? If I use the maximum likelihood estimator, I have to encode it. Note that it takes values in the set 0, 1 over n, 2 over n, until n. There are n plus 1 possibilities because the maximum likelihood estimator is just a frequency of 1s in your set. So I need about log n bits to describe the maximum likelihood estimator. Now, it turns out that if I slightly truncated this estimator, so I don't take the frequency of 1s, but some number nearby, which I encode with less precision, then if I code the data using that truncated maximum likelihood estimator, I use hardly any bits here, a constant number, and I use 1/2 log n, I win 1/2 log n bits here. So here I need a lot less bits, here I hardly use anything, and you can calculate that the total number of bits I need to code the data will be smaller. So what happens here is the MDL estimator tells me if I calculate things, basically to take on the unit interval a grid with 1 over square root of n. And then, so if I encode a value on that grid, that means there's square root of n possibilities, and log square root of n, which is 1/2 log n. Bits to encode any value in there if I use a uniform code. So then I need 1/2 log n bits to encode theta, and if I always encode theta, which is closest to the maximum likelihood estimator, then the number of bits needed to code the data based on theta hardly goes up than if I would have used the maximum likelihood estimator. So it's still nearly as good there. We can show that something like this is the MDL estimator. In fact, once again, you have to correct for the curvature of the model, which in this case means that your grid should be a little bit more dense here at the boundaries than in the middle. And the density should once again determine on Jeffrey's prior. Now this may seem like a very bad thing to do. I should cut off the maximum likelihood estimator. It's like you're losing information. In fact, it turns out that this in practice often for small samples works better than the maximum likelihood estimator. Once again, a similar phenomenon to the phenomenon that's observed for EM with early stopping. If you make your search space smaller, you run less risk of overfitting. If you want to select a number of parameters, it's obvious that maximum likelihood will always select the most complex model and will overfit. Even if you have a parametric model, it turns out that for very small samples, maximum likelihood can overfit a little bit. If you do this, you overfit less. Doesn't mean, by the way, that this is the best estimator to use. I think there are better estimators. I wouldn't use it in practice, but it is better than maximum likelihood estimator, although it looks a lot worse. So, yeah, I guess I should do this after break.